Hello and welcome to episode 2 in the series Particle Physics 101. And today I'm going to be talking about wave particle duality. Wave particle duality is a concept in quantum mechanics that proposes an idea that all particles behave as waves and all waves behave as particles. So you can think of it as all units of matter possess properties of waves and particles. But before I really talk about how amazing this is, let me talk about how it was originally thought of. So first we must go back to the 1900s, when a German physicist by the name of Max Planck was doing something quite amazing. So at this time we already had the knowledge that light has different frequencies, but we did not know that light was composed of photons. One other thing that Max Planck knew is that the energy of a light wave is directly proportional to its frequency. So this would be how it was written in mathematical terms. But they weren't exactly equal, because the energy of a light wave was significantly lower than the frequency of it. But how much lower is the question? After what I can only assume is a lot of experimentation, he finally found the answer. This proportionality constant, you can think of it as, is known today as Planck's constant. The value of Planck's constant is 6.62 into 10 to the negative 34 meters squared kilograms per second. So as I have mentioned, a very small value. But why such weird dimensions? Meters squared kilograms per second. Let's try and evaluate that. If we were to do a little bit of dimensional analysis, like it is called, we must have joules on the right side of the equation, because the left side is equal to joules. So let's try and do that. So we have joules, you can say. So H is meters squared kilograms per second, and frequency is cycles per second. Cycles is not really a defined dimension, so you can think of it as distance, another unit of distance. Okay, so if we just join these together, we can get that right over there. Now what can we do from this? One thing that we know is that one Newton equals kilogram meter per second squared. This is simply brought from F equals ma. So we can actually take those things out and we can say kilogram meter per second squared multiplied by meters times cycles. So kilogram meter per second squared can now be written as newtons, and meters is a unit of distance. Cycles, once again, is a unit of distance, so you can say distance. And voila! Joules equals, well, joules. So this is how we can conduct dimensional analysis, just to test that these dimensions that we have used are actually correct. Okay, so this is all well and good, E equals HF, but how does this prove wave-particle duality? And how does this have anything to do with the content of this video? That will come in 1905, when Albert Einstein proposed the photoelectric effect. And yes, this is also when he released his special relativity paper. The photoelectric effect, in a nutshell, is if a light wave was to hit a metallic sheet, obviously of certain properties that I'm not going to get too deep into right now, there will be electrons that are bounced off of it. And that is, interestingly enough, how photovoltaic cells work, or solar panels. But more importantly than the fact that, oh, an electron is given out, he proposed something far deeper than that. He proposed that light, which was originally thought of to be a wave, has particle-like properties. And this is, you can think of, the first introduction into wave-particle duality, the initial understanding of this entire concept. Then in 1924, Louis de Broglie, a French physicist, wrote in his thesis something that would change quantum mechanics forever. He understood wave-particle duality didn't only apply to light, but to all fundamental units of matter. So how did this really happen? The first understanding was when people started to question the momentum of a photon. Well, now we know that photons are actual particles. They must possess some momentum. But as we know, momentum equals mass times velocity. Have to put the vector symbols there. And if the mass of a photon is 0, doesn't that just mean it has no momentum? But how does that make any sense? And that is where Louis de Broglie came to the rescue. So let's try and figure out what he really did in this scenario. So one thing that we also know, proposed by Albert Einstein in 1905 in his special theory of relativity, the very famous equation E equals mc squared. So if we just rearrange this, we can also get that m equals E over c squared. So putting that in the momentum equation, we get the momentum. I'm just going to drop the vector signs for now because we're not dealing with any mathematical rigorous proofs. I'm just roughly explaining it. Equals energy over c squared times v. And in this case, we're going to assume the velocity is the speed of light because we're talking about photons. So c. Therefore, we can get that P equals E over c. Another thing that we know over here now is that E equals hf via Max Planck. So now we can say the momentum equals hf over c. Now what else do we know? These are just a lot of equations being put into a single one. We also know something really interesting, that the wavelength of a wave equals the velocity divided by the frequency. So in this case, the velocity being c, we can finally get our equation of momentum equaling h over lambda. And voila, this is the momentum of a photon. But more correctly, I should say, this is the de Broglie wavelength. And this is what finally made physicists and people understand that all particles have properties of waves, and all waves have properties of particles. Now this is an incredibly important concept to understand because this really reshapes our knowledge of quantum mechanics in general. I'm going to be talking a lot about wave-particle duality in this series because a lot of concepts in particle physics and quantum mechanics depend on this idea. I hope you enjoyed this video, understood a little bit something from it, and until next time, stay sharp.